Welcome to our second module of Geology 3330, Geomorphology. In the second module, or in this module, we are going to talk about the way in which sediment is transported in the stream. We're then going to look at the different types of streams that you have, and we're then going to look at the sedimentary features that are on the floodplain. I would now like to shift to the PowerPoint presentation. I would like to start our discussion today with this image of Templeweep Canyon. In the bottom of Templeweep Canyon, you see the Virgin River, which is has cut its way through the canyon. You see the effects that we talked about last time of downcutting, slope retreat, and headward erosion in the headwaters of Zion National Park. We are now going to look at how the fluvial system and how the collection part of the system collects water and how it transports sediment. The first topic in our discussion is the topic of sheet flow. Sheet flow is when water falls in the headwaters of the drainage area, flows down that drainage, down the slope, and it flows along a flat surface. If you look at the area here in this image in the lower left of Maple Mountain, you'll see here in the foreground that you have a very distinct flat slope that's the water is flowing down. If you're looking up here in the drainage collection area at the top, you will see that water flows down that slope, and that is where the sheet wash portion occurs. It usually occurs in the headwaters of the basin. It is much more predominant in the desert areas, and oftentimes it produces rills. If you look at this water flowing down this road, you can see up here it's flowing as a sheet, and as it comes down, it begins to come into ripple mark type features, and those ripple marks are what geologists and what geomorphologists refer to as rill marks. This flowage down this road is picking up sediment and picking up parts of that asphalt and moving them on down, and eventually it will hit the stream at the bottom. The sheet flow flows down until it hits a low area where it enters the stream drainage and then begins flowing downhill. The next thing we need to talk about is when the sheet flow hits the drainage, it then hits the center part of the drainage basin and starts being collected. In this area, you typically have an area where the stream channel is the active stream channel, and you can see the image number 1 has an active stream channel. You then have an area that during high flow, during the spring runoff or during floods, the river will go up and occupy that area. Along the margin, you will see in the lower part where you have natural levees. Natural levees are the banks that are along the river. For those of you who live here in Nacogdoches, if you go down along Lanana Creek in Pecan Park and walk along the Lanana Creek Trail, you'll notice that you are walking along natural levees. When it rains very heavily here in Nacogdoches, the water comes up and goes over the levees and spreads out through Pecan Park, producing the features that we'll talk about later of splay crevasse deposits, and leaves a thin layer of mud representing aggregation of the floodplain and aggregation of the levees, like are shown in the third diagram. The other major concept that we need to talk about is the concept of longitudinal profile. If you look at the diagram at the bottom, you will see starting at the mouth of the river and going all the way up the head, you have a curve that it represents an increase and a greater and greater increase in the slope of a line. That is called the cross-sectional profile. When we look at this cross-sectional profile, the term that is oftentimes referred to it is the Thalweg line. The Thalweg line runs along the deepest part of the channel. If you look at the diagram we had on the previous slide, that would be along the center of that channel. It is usually marked by a blue line, and it has deep and shallow places along that channel. Those of you who like to go swimming in the river or like to go fishing in the river are very familiar with these deeper holes that represent part of the erosion that is there. The meandering pattern that you typically see in rivers is produced by the Coriolis effect, or the spinning of the Earth on its axis, which sets up a harmonic action that produces a sine wave down the river. That sine wave is translated into a river that bends back and forth and is not constant. When we look at the river stream, we have to look at the velocity of the river stream. 1/4 of the depth of the river is the maximum velocity. And usually in a straight segment of the stream, it will be in the middle of the stream. You can see the diagram in the upper right middle. You have a diagram showing the velocity vectors in a stream. The hole in the center tells you that this diagram shows the stream flowing towards you. If that were an X, that would indicate that it was flowing away from you. The old tale that I was told when I took geomorphology years ago by Ken Hamlin was that if you stand there and you see an arrow coming towards you, all you see is the round tip coming towards you. If it's flowing away from you, all you see are the feathers, and that's why the X is there. Again, let me emphasize that the meandering of the stream is produced by the Coriolis effect, which produces the meanders that you're seeing. The discharge of a stream can be calculated in meters cubed by taking the width of the channel times the channel depth times the average velocity. When we talk about stream erosion, a stream cuts the valley through which it flows. Now remember, in the first segment we talked about down cutting, which is the stream cutting down like you see right in the bottom of the channel. We talked about slope retreat, where the water falling on the slope, you can see, forms a type of sheet flow that goes down into the river. And you have headward erosion, which up in the headwaters, more and more sediment is being eroded there, and that will produce in a drainage basin and cause the drainage basin to expand. When it comes to the stream, a stream erodes by hydraulic action, which is the ability to pick up and remove rock. It can also erode by dissolution or solution activity, where it dissolves the rock, and it can also develop the channel by abrasion or dragging rocks along the bottom. One of the unique things that is always discussed in geomorphology class is the concept of a pothole. A pothole is when you have a flood, and that the flood waters or river waters take rocks and twist them in a circular pattern showing the helical effect, and the rocks literally grind a hole down into the rock surface. When it comes to sediment transport, we need to talk about sediment transport. Usually in sediment transport, there are 3 different processes that are operating. The process of bed load first, second is suspended load, and third is dissolved load. To look at the bed load first, bed load is further divided into rolling load, traction load, and saltating load. Rolling load is where the clasts are rolled along by the water. Sliding load is where and gliding load is where it's dragged along the bottom, and saltating is where it bounces along the bottom. Now, within any stream, you have 2 processes that happen when the stream starts to flow. One is you get laminar flow that occurs when the water first starts to move. The water molecules are moving horizontally. When they encounter a rock, they are deflated off and start to form a helical pattern, which is produced by the Coriolis effect. If the volume of water gets faster and faster, they go from what is known as lower flow regime, which is basically laminar flow or the flat lying flow, and turbulent flow, which is picking up the clasts, to shooting and plunging flow. And oftentimes when we talk about the Reynolds number and the Froude number, those are numbers which represent the start of water flowing and the start of going from lower flow regime to upper flow regime. Next, we talk about suspended load, which are those particles that never touch the bottom. The water velocity is great enough to keep them in the water column without needing to bounce. And the last is dissolved load, when the water most water is slightly acidic, so it will dissolve all calcium carbonate and many other things, iron oxide, for example, and transport it in a dissolved form. Next we need to talk about stream deposition. When we talk about stream deposition, the important thing that we need to talk about is the point bar. When a stream goes around a bend produced by the Coriolis effect, it slows down on one side of the stream channel and speeds up on the other. This produces the point bar that you see there on one side, and the cut bank, which is on the other side. If you look at the river on the lower right, you will see that you have a beautiful example of a point bar. Typically on a point bar, if you look up at the head of the point bar, you're going to see chutes, which are narrow channels up in here. You can see the chute right up here on the top of the diagram of the point bar. Within any fluvial system, there are two different types of bars that are recognized. One type is the midstream bar, and the other type is the point bar. Now, midstream bars are produced when velocity drops and allows sediment to be deposited in the middle of the stream. And that eventually leads, as the river level drops, to what is called a braided stream. A meandering stream is a stream which has sufficient water to allow the helical forces of the Coriolis effect to allow the stream to move back and forth and produce the bends in the river. When we look at braided streams, this image that you see here on your right is from Denali National Park in Alaska. If we look at the second type is the point bar system, and if we look at the features there, whenever the stream meanders due to the Coriolis effect and has helical flow going down through it, what happens is you get bends. When these bends get too tight, they will cut off the bend, and that produces a channel cutoff or a meander cutoff and leaves a abandoned oxbow lake. And you can see in the image below that you have a number of oxbow lakes in here. The other thing we need to talk is, how do you go from a braided stream to a meandering stream? Well, I'd like to use an example from Mark Twain. When Mark Twain wrote both Huck Finn and Tom Sawyer, you ask what time of year it was. Well, it was the summer, because in both cases he describes paddle boats avoiding the midstream bars. Midstream bars and braiding in any channel occurs when you have more sediment and a very low water volume. A meander stream occurs when you have an intermediate amount of water, and your entire floodplain is covered when you have a huge volume of water. The braided stream favors coarser sediment and a higher sediment load. The meandering stream favors a finer grain sediment load. Well, in conclusion, the major points that we've talked about in this module are: 1, what type of flow patterns do we have, with the fastest flow pattern being in 1/4 of the channel depth. When you go around a meander bend, the speed shifts as you go around the meander bend. The meandering in a river is caused by the Coriolis effect. We then talked about the different types of deposits that are on the floodplain, and we finally ended up talking about how you go from a braided stream, point bar spring, braiding up to a meandering stream. Well, it's now time for you to go to D2L and answer the questions that are there. Also, in this section, there is a discussion question for you to go and think about how you go from a braided stream to a meandering stream, and write your reflections, and then you will need to answer one of the other students' reflections. Well, we will see you next time. You have a good day.